good.
I do have one question about this phosphorus and fluoride. So is the reason it's not polar that they usually cancel each other out going
Yeah,
that
so
way?
all of
Because
them,
typically like that, they're both kind of movements, they cancel each other out. But on here, it has this kind of asymmetry that these kind of combine as one.
yeah,
That, like,
exactly, because,
cancels out.
yeah, if you're adding vectors, I should say,
Right.
it cancels out, or they cancel out in that direction.
Of course. Yeah, that sounds right, because it was pretty small, right?
Yeah.
That looks good, although this polarity looks a little small. This looks small. That looks weird.
Yeah.
So your moles looks okay.
So this is the milliliter?
Yeah, so this should be in milliliters. So let's see, because we should take this moles. 8, right, 1, 2, 3, 4, 5, and divide it by, and then we have to convert that to liters, so 0.02. 1. So yeah, that should be your molarity, so I think that'll make
Better
lot,
sense.
yeah.
Thank you. That's what I was wondering. So we have to change liter. Thank you.
I don't think I have any handouts. Because there's no lab. It's too scary.
I guess I should go leave this week.
I don't know, they had already started, I don't know. They were like a big camera.
But we don't have lab today?
Like.
Yeah, no lab. You could have listened. Yeah, we'll do review. I'm just letting y'all check out because there's supposed to be that open forum, which should be good, although I don't know, the reports are. You gotta barge in there. No taxation without representation.
wasn't efficient. The ionic equations, is it just like, because I was looking at this one, is it just like determining whether it's a positive or negative, like, charge?
Yeah, so the idea is you cancel out what are called like the spectator ions that aren't doing anything. And so yeah, for your like, they abbreviated it kind of funny. But you just have, since your potassium's your spectator, since it's just like ions in solution, right?
Yeah.
The only thing you care about is just like, you can even simplify it to the hydrogen, like H plus OH gives you water, because that's like essentially what you're doing. They're just showing
So it's just
the
like
salts, yeah.
how to get the end product kind of thing?
Yeah, and you just get rid of whichever ions would be the same on each side, so that they're like, if they're dissociated. So that's why they got rid of the K there.
Okay, so for the vinegar on the other page, right, so I guess somewhere in here. So this one is for, well, this one is for,
Yeah, so the
Vinegar.
vinegar, so you could write it, let me see if I can mark it. So you have your equation, so you do your double displacement. But then this is just aqueous, right, ions in solution. So you could formally to separate it, they say like, oh, rewrite everything as an ion that disassociates. And then you cross out what's the same. I'm gonna associate this too. So then you can just cancel this out, and then you're just left with HOH basically.
goes, oh. Thank you.
see. I'm trying to see if we're still missing people or not from the forum. Oh, I hear people coming. Hello. Did you go to the forum? I thought you were going to represent Earth Club and all the things of the student fees. And I'll let you guys duke it out later. All right, let's go into our midterm, but before we do our midterm review, so just a reminder, so no lab this week. Yeah, it's on the syllabus, so I try to do that if I can. So next quarter, I haven't made the syllabus, and I'm not sure if I can fit in a free week. We'll see what happens. But I try to do that so you have like a week to catch up. So if anyone needs to make up a lab, this would be a good week to do it as well. I don't think anybody's in that position in here. But it also just gives you extra time, and so if people have more questions, we could definitely meet during our kind of lab designated period as well for office hours. And then if you want to catch me tomorrow, just make an appointment. I can be available as well. So I'll just say Wednesday by appointment. All right, so let's look at your final. We'll do some practice problems. Or not final, but midterm. And I know. So it starts off with some multiple choice questions. I think I'm going to add a few more though to kind of help buffer you guys. Easy stuff.
What do you think?
I get them all wrong every time.
They're supposed to be easy. So for multiple choice questions, I would expect some like phase diagrams. And so like labeling those, so solid, liquid, gas, right, your phase transitions.
Have you ever heard a class ask for more word problems?
Usually not the word problems, yeah. And then, so, right, this would be both your kind of triple point diagram. And oh, I kind of drew that upside down. I cannot draw. Oh my gosh. So, right, this diagram and also our other kind of energy phase diagram. So being able to label those, and again, labeling kind of the transitions. So we mentioned anytime there's a plateau, there's a state change. And then don't forget these lines too. So remember every kind of border is also a state change. So right, those are sublimation, solid, liquid, gas. So all those. So you might have to label something like that. So I'd label like points and areas, or also labeling like this diagram, like what's the state of matter down here. So if this was, ice, that would be solid, liquid, then gas. So that sort of thing. And so just expect multiple choice questions on just like basic kind of concepts. So there's a question about kind of gases. Expect a colligative property question. Let's do that. Sorry, I have too many things open. So let's do a practice. So we have a 0.3 molarity solution of iron 3 chloride. So what is the colligative molarity? So I'll give everyone a minute or so to look at that. So what do we get for this problem? What do we kind of have to find too? What was that factor called?
I know it's represented with I, can't remember.
So I heard some I's, so that Van Hoff factor, which we don't have to know the names so much, but we just have to know what to do with it. So what's our I, or basically how many particles do we get in solution? Yep, so 4, right? So we disassociates into iron 3 plus our 3 chloride ions. So I is 4. So then for our colligative molarity, we just have to multiply it by our Van Hoff factor. So then what do we get for this one?
1.2.
So 1.2 molarity.
Where are you getting that from?
So 4, we just had to count up like effectively how many ions there are. So once you establish that it broke into 1 iron and 3 chlorides, then it's just 1, 2, 3, 4 total particles. Yeah, so that goes back to, right, like the non-electrolyte, so sugar is always our classic example. That's just 1 because it doesn't dissociate, right? Sodium chloride was 2 since we have just the anion, the cation. Yeah.
What does this colligative molarity represent?
So this is just like our answer, right? Colligative molarity, but all the properties that are related to colligative molarity. So that's freezing point depression, boiling point elevation. What else did we mention? So all these, just how like the vapor pressure is effective, right? All that are considered colligative properties. Back to our. And so other kind of multiple choice questions. So be familiar with all like your compounds, so like the network covalent solid, ionic solids, right? All the classifications. I'll put classification of matter.
That's like chapter 15, right? There's different types of solids.
Let's see. Oh. I don't remember. I think you're right though. We can.
So I think just when you talk about the metallic crystals,
Oh yeah,
crystals and their structures and properties.
good memory. So yeah, all this, so classifying our crystalline solids, so our molecular solids versus ionic versus atomic solids, so the non-bonding metallic and network covalent. So that's just a multiple choice question. And then there's a little bit of trivia that I think comes from like those inner chapters. So I don't want to give everything away, but let's just answer this. So what is the common oxidation state of silver? So what is silver normally? So +1. So use that info, and that might help you with some of those multiple choice fun fact stuff. And so we'll give away one of these kind of multiple choice. So let's just answer this. So which noble gases make compounds with fluorine? So which ones do we remember? Do we have any thoughts? So xenon for sure. So we remember which ones, what compounds were those of xenon? Do you remember? So xenon, there were like 2 examples. There might be one with like iodine, like IF3. But do we remember what the 2 xenon fluoride compounds were? It 4 and then 2 were the other ones. And so to answer, because you don't know what the multiple choice question is, but okay, let's look at the periodic table for a second. And so what do we notice about xenon on our noble gases, and why does it make compounds with fluorine? Do we remember? What was part of the argument?
Something to do with how large it is, and then it's got a small ionization energy.
Exactly. So it's mainly a size argument that we go with. And so if it's asking what noble gases can make compounds with fluorine, so we have xenon, and we said, well, it's pretty large, and we can add that, right? So it's basically large diffuse orbitals, and so they can mix. And it's also a size thing, so it has plenty of space, too, for the fluorines. And so what other noble gas, so who's right above it then, if we're going with this size argument? So what's the next noble gas? So krypton is the next one that's on there, so the next largest, so right, xenon's larger, and then krypton is our next smallest. And so krypton is our other example, at least more commonly. So this would be kind of the other compound. And so krypton difluoride is known. And so I would just stick with these 2 for kind of the known ones. And then the rest of the ones, like, you know, neon difluoride, those I think just exist in theory. So I don't know if they've actually been synthesized, since those have a lot of steric hindrances. So that's why we don't see a lot of compounds. And also, of course, right, the octet rule. But anything that will make a compound is going to have to have a large diffuse orbital. So that's xenon and krypton for that one. And then, so multiple choice, looking at the rest of the ones you'll have. So some sort of boiling point trend. So, right, think hydrogen bonding and all that. So hydrogen bonding is obviously going to have the highest boiling point, and also the number of hydrogen bonds matters. Again, think of the alcohol versus water argument. So water has that higher boiling points with those 2 hydrogen bonds. Let's see. So let's look at other types of problems. And so if we think back to the beginning of this year, we were doing kind of structures and determining how many bonds and their hybridization. And let's label these. So carbon 1, 2, and 3. So for this, determine the total number of sigma and pi bonds, and then also determine the hybridization at each of those carbons. So carbon 1, 2, 3. All right, so take a minute or so, kind of look through this. Might want to redraw it too more explicitly. How's our answer coming along? Maybe more time? Okay. And so if you're stuck on this problem, I would at least start by kind of drawing it out more explicitly. So we have our carbon 1 double bonded to our carbon 2 here. And then notice carbon 2, so it only has 1, 2, 3 bonds, so it needs a hydrogen. And then our carbon 3 here. So that's fine, triple bonded to nitrogen. And so now this helps us. So maybe we should start with our total sigma and pi bonds. So how many total sigma bonds? And so that would be counting up, right, all your CHs. So I hear 6. So what other people got? Excellent, right? So every single bond, so we can write this out. So it's 1, 2, and then this is a sigma 3, 4, 5, 6, right? Because one of these is a sigma. And so what about our pi bonds? How many pi bonds are we left with? So 3. Is that what everybody got? And that sounds good. So then that's just going to be your double and triple bonds. And looks like Chet has the same answers as well, so that looks good on everyone's end. And then what about our hybridization? So again, this picture is probably more useful than just trying to look at this one. So what do we get for hybridization for C1? So sp2, and again, 3 orbitals, 1, 2, 3, and then it's attached to 3 things, so 1, 2, 3, so that helps. What about C2 here? So sp2 as well, excellent, and again, don't let that hydrogen trick you that they didn't draw it. And what about this last one? So sp. So we have a question in the chat of just how do we do our hybridization. So I think the easiest way to do the hybridization, yeah, is this cheat sheet. Where was it in the notes? I'm trying to remember what chapter. 9, maybe? 8?
Right off to the side of this, like sp hybridized for the 2 electron pairs, sp2. Yeah.
So people in class are also saying, so everyone likes this kind of Vesper cheat sheet. And so remember, it just corresponds to their electron pairs, so that's how many things are attached. So that could be either lone pairs or atoms. And so if we have 2 electron pairs, it's sp hybridized, 3 things attached, sp2, 4 things, sp3, and kind of so on. So the parent geometry kind of gives you the hybridization. Yeah, so the hint in class is everybody kind of wrote this down, I think, to kind of help. And if anyone in class needs this printed out, or I'll send a link in the chat as well, so you can print it out. That compound chem is useful. All right, other questions about this problem?
Can we go over the cis and trans isomers again? I have a general idea what they are, but I just forgot.
So we have a few different cis isomers, right? So we can either have what I kind of call our OChem cis and trans isomers. So that's just any sort of like these double bonded structures generally. And they have, so this would be a trans isomer where they're on opposite sides, kind of the main group. So in this case, I drew it as a methyl, right? You could also draw something like bromine and bromine. So 1, 2, 3, we could add in like a methyl group, right? This would still be trans. And then anything on the same side is cis. Or we could add like a bromine in or something. So still cis. And kind of the key with this one is there's a double bond, so no rotation.
Does it have to do with the fact that double bond makes it a resonance structure? Or is that separate?
So that would be separate. So here, right, we don't have a resonance structure, so there's nowhere. But it is, so the problem is, right, we have that pi bond, so that's a through space, so it's not going to rotate. So that's what prevents it from rotating. And then we also had, though, what I would call like our inorganic cis and trans isomers. So we could have it both in these square planar structures. So we saw like a platinum and, oops, sorry, I drew the trans one. So fluorine, fluorine, where they're kind of next to each other, and chlorine, chlorine. So that would be cis, and versus where they're across. So that would be trans. And then don't forget the other, so this is right square planar geometry. And then versus the octahedral inorganic. And so this would be the form A, X4, Y2, where you just have two different substituents, and then they're different on the cis. So let's do tungsten. So, right, this could be one cis isomer. Obviously, this chlorine could move around, right? That would still be cis. Versus the trans, where the chlorines would be across from each other. Does that kind of help clarify the cis and trans isomers? And I know it's kind of confusing because we touched on all of them, of kind of like the OChem versus the inorganic chemistry. Did you have a question? All right, let's try, we'll switch gears now and do a more mathy gas law question. And maybe I can type this out. So what is the molar mass of a gas if 2.14 grams, and I'll make it bigger, of the gas occupies 156.0 milliliters at a temperature of 170 degrees Celsius and a pressure of 857 torr? So what formula did we use for this one? What did you say, the gas laws? Which one? So ideal, so PV equals nRT. So that sounds good. And remember, right, our gases, we only really have two formulas. So either the PV equals nRT or just kind of rearranging it, right, into the P1V1 equals N1 T1, etc. And the only tricky part about this problem is they were also kind of mean here and didn't give it to you in any like normal units, I would say. So now we have to convert everything. And so I'm seeing in the chat that somebody put that 170 degrees Celsius is 443 Kelvin. So I think that helps us. And so we need to convert this milliliters to liters. And then torr to ATM. How many ATM did people get? I have 1.128. That sounds good. Is that what other people got? So let's see. And so we're solving for, so what do we have to solve for first? So moles, so solve for N. So let's plug that in. So I get this answer for my moles, so 0.0048, I guess I'll round it to 4. Is that what everybody got? Excellent. So now what do we do with this number? So it asks us for molar mass. We're given grams, though. Is this many moles? Yeah, that sounds like a good plan. So for the chat, right, let's set up a proportion so we can do 0.412 grams is equal to 0.00484 moles. So X is equal to 1 mole. And then you can just cross multiply and solve. So then that gives us 0.214 divided by our moles. And so do we get this answer?
I wanted to ask, I got a very similar answer, but I went about it a different way, where I used the density of an ideal gas equation. The density equals NP over RT, and then just used the R value that has to do with torque rather than units of atmospheric pressure. And I got about like 44.
Yeah,
0.2.
that works. So yeah, there's probably more than one way to solve it. So yeah, that sounds like a good approach. I just tend to stick to the like PV equals nRT.
Yeah, I just saw the grams and the
Yeah.
moles there, and I'm like, I feel like I have to use the density.
Yeah, that's a good technique as well. All right, other questions on this one? So let's try another problem. And so like I mentioned, you'll have kind of a, well actually, so you can look at your quiz that you just got back. And it was kind of a mixed bag on how people did on the quiz. And I'm mainly talking about question 2. So most people actually did really well on the quiz. Chapter 15. So the quiz that we just got back, the question that people had the most trouble with was 2. So there were a lot of 8s, so people had trouble with 2 and 10. And so the problem that I found with 2 is that people just like forgot half of the problem for the most part. So like if you didn't get the answer, so we'll kind of go over the quiz, but then we'll do like a better practice problem right now. So right, the quiz was something we have 0.25 moles, and we want to warm it from 22.5 degrees Celsius to 0, and then it said then melt. And so you had to first change it, and so what was funny is I also gave you the heat capacity in kind of different units than maybe we were used to. And I would expect, again, you have to watch your units on your exam. So we were given joules per mole Kelvin, but remember Kelvin goes up the same. So then our first part, right, was Q, MC, delta T, but except, right, we didn't really have mass, we had moles instead, so that was kind of tricky. And so then we did 22.5 times our 0.25 moles. So that's our delta T, our moles, and then our, blank, times 37. And then this was in joules though, so that was also tricky. So divide by 1,000. So now we're in kilojoules. And so that was A, so some people circled A as the answer, but we only brought it up to 0. We didn't do the state change. And I don't think people got tricked on that, but I did give out a lot of extra information like the delta H of vaporization as well, but we only needed the fusion, so the 6.01 kilojoules per mole. And so then that was just 0.25 times your 6. And then plus our 0.212 from before. So it should have been C was the correct answer.
I guess what I was thinking is that in the actual equation to do this, like the written equation that we have in our notes, it's for Kelvin temperature and not Celsius?
Well, remember, Kelvin and Celsius go up by the same +1, -1. So whatever your delta T is for Kelvin and Celsius is the same.
So you don't have to.
Yeah, you don't have to like convert or worry about it. Yeah, it would only be if you were given it in Fahrenheit, which I won't do to you. But yeah, otherwise it's just up the same amount, which is convenient or not. All right, so let's try another one of these, because like I said, you're going to have one on the exam, and it won't be water, and it's not going to be, so we're going to do acetone right now, so it won't be acetone. So let's do the problem. So we're looking at acetone, and you need to have some data. And Again, this is how your exam question might be structured. So you'll be given freezing points, boiling points, and then any relevant information. So our fusion is 5.7 kilojoules per mole. Delta heat of vaporization is 31 kilojoules per mole. The heat capacity, and so this is all the states, so gas is 75 joules per mole. Heat capacity liquid, 125 joules per mole. And heat capacity solid. And so now for the actual question. So how much energy is required to take 1 mole of acetone from negative 100 degrees Celsius to 25 degrees Celsius? So take a couple of minutes to work on that. Again, right, look at all your relevant information, what's going on, what do you need from here, and we'll go over it. So let's start hearing your thoughts. So what do we do? What do we start with? Lyra?
We could start by finding the change in temperature as the acetone goes from its initial state of negative 100 degrees Celsius to the freezing point, negative 4.9 degrees Celsius.
So that sounds good. So did everybody hear that? So you said let's start from negative 100 degrees Celsius, but then you had to notice that the freezing point, right, is pretty close. So negative 94.9 degrees Celsius. So let's calculate how much energy that took. So something like Q equals MC delta T. And so we have our heat capacity, except we should kind of change this to moles given our formula here, or what we were given, right? So we weren't given heat capacity in grams, but rather in joules per mole. And so now we can take this, so we have 1 mole times, and then our heat capacity. Which heat capacity do we pick? So solid, so 90 joules per mole, so moles cancels, then I need my delta T. So I think that's about 5, but 100 minus, so 5.1. So do we get 459, so joules, so that would be 0.459 kilojoules. All right, so now what do we do? So we're at kind of the freezing point, melting point. Melt it, so state change time. So right now we're melting. Okay, we need the heat of fusion. And so now let's do our state change. And so again, right, grab our fusion value. And it kind of helps, right? If you ever mix them up, well, fusion should be the smaller number. It comes first, so that also kind of helps. So 5.7 kilojoules per mole. And we have 1 mole in our problem. So that gives us 5.7 kilojoules.
Is fusion always lower?
I don't want to say like always, because there's always that one exception, but yeah, like for the most part, it should always be lower. And we saw that just, with the amount of energy it takes to separate those gas molecules. So that's why we always expect it to be lower. All right, so now we did our state change. We're still at negative 94.9. So now what do we do? So take it up to 25, and so that's under our boiling point, so we don't have to worry about any other state changes. So let's just do that. So negative 94 point, I already forgot, 9 to 25 degrees Celsius. So I'll find my delta T. So I got a delta T of 119.9. And so now our Q is our delta T times our 1 mole. And so what heat capacity do we use now? Exactly. So make sure you choose the liquid one since we did the state change. So 125 joules per. I should have put the unit as mole Kelvin. That would be more useful. All right, and do the math. So 119 times 125, and then let's put it in kilojoules. So do we get 14.9 or about 15 kilojoules? So 14 point, I'll run it to 99 kilojoules. And then if we want our total energy, so now we just have to add everything. So 14.99 plus our melting, I'm gonna skip that, plus 5.7 plus 0.459. So about 21.1 kilojoules total. All right, questions on that one?
Oh, wait, for heat capacitance in moles versus grams, it doesn't really matter as long as you use the corresponding ones. You can swap out that value in the equation for either moles or grams as long as you look at whatever value you have.
Yeah, exactly, and this is probably just whatever I found online, which is why I switched units, because like, you know, usually I go to, I think it's like the NIST website, the International Standard Table, and so yeah, I'm just kind of basing off of what I can find, and it's just whatever they give it to you, joules per mole or joules per gram. When you start looking at like substances, like I was for your exam, it's harder to find like all the information. Yeah, but and you can like do the conversion, right? So you could rewrite this in a joules per, or grams per mole if you did like the math conversion, but. Right, yeah, but. All right, let's try another type of problem. So I think you had one on your homework maybe that was like this, but it will come up on your exam, so we should practice it. So we have a solution of a non-electrolyte. The osmotic pressure, at 30 degrees Celsius of this solution contains 0.455 grams of compound in 1.00 times 10 to the 2 milliliters of solution. And the pressure is 65.5 millimeters of mercury. So what is the molar mass? how's this problem coming along? Did we find the formula for it? So I'll give a hint on the formula, because it's this one where the osmotic pressure is I molarity RT, which we admittedly kind of rushed over in class, so this might be useful.
Is that a little table? For us,
It's apparently uppercase pi, but yes.
Oh yeah, it's pi, big pi.
And that's the same as like pi equals RT colligative molarity.
Yeah, so the I and M, all of that is colligative molarity. So I is just, yeah, like effectively your colligative molarity. So that might help. And then R is our gas law constant. Yeah. So we will have to convert to Kelvin though, because of the gas constant. Yeah. All right, so coming together, sounds like.
where do we get the osmotic pressure from?
So that one will be this pressure, the 64.6. Yeah. It does, yeah. So that is the next trick. All right, so let's see how your pieces of this puzzle are coming together. So we have to use this formula relating the osmotic pressure to our effective molarity times our RT. And again, R is just our gas constant, so that means T has to be in Kelvin. And so again, if we're using this gas constant, then we have to convert the pressure to ATM, which you guys caught on with. So, excellent. So then I get 0.085 ATM. And so, right, this is our osmotic pressure, or big pi, or table. And so now we can set up our equation. So 0.085 is equal to, and so in our case, right, the I is 1, so we can get rid of the I, right, because it's a non-electrolyte. So I equals 1. So now we're just left with MRT. So we're solving for molarity, and our gas constant times our temperature. And so then do we get something like molarity is equal to 0.00342? And so that's moles over liters. And so now we can start solving for things. So where should we go from here?
Then we could find the moles in the solution by putting 0.1 liters, because it's 100 milliliters of solution.
So then multiply by 0.1 liters to give us moles in solution. So 341 times 10. So that's 1, 2. Did I do that right? So 3.42 times 10 to the negative fourth moles, is that what you got for 100 liters? And so then, right, we could set up a proportion again or something. So we have 0.455 grams of compound is this many moles, or grams per mole. So then what do we get for our molecular weight? So 0.455 grams, so 1 mole. So we could set up a proportion like we did, or divide. So do we get this answer? And then you can always double check yourself. So 0.55 divided by our molecular weight, so that's moles, divided by 0.1, so then we're back at our molarity, so that looks good. So X is 131, or I'll round it to 132 grams per mole for that one. Is this liters? I put it over liters, yeah, sorry. Bad handwriting. So liters. So that's just our liters canceling out to give us moles in the solution. All right, there's kind of 2 things left on the exam to go over. So I'll kind of let you tell me what you want to go over. So of course there's going to be an MO diagram on the exam. So I would expect to make a MO diagram. So do we want to practice an MO diagram or the other problem? And so some of these, this one will not be a bonus, but there's also going to be a bonus having to do with like the cubic structure thing and finding the volume and the sides. So I don't know if you want to try the cubic one next, and then we can always revisit the MO diagram. All right, so let's do that, and then we'll give a quick and dirty on the MO diagram. So let's try our cubic. And so let's try, so we have element X has an atomic mass of 50 grams per mole, and it is a simple cubic structure. So assuming a sphere, determine the volume of a single X atom, and we'll do it in cubic nanometers, so nanometers cubed, and I'll at least give you the volume is 4/3 pi r cubed for a sphere. Oh, and I forgot one other thing, and the density, sorry, is 3.7 grams per centimeters cubed.
It says right there you want to keep it millimeters cubed.
The final answer is in nanometers.
I think you should give us, yeah, can you give us the first, like, equation that we're supposed to use?
Well, let's see, you guys tell me. So we have atomic mass is 50 grams per mole, we have a simple cubic structure. So what does that tell us?
Because that's 3 times.
So one atom, okay. And then we're given this thing, and what about density? So what can we do with density? So I think you have the right idea. So you're take the 50 grams and divide it by a mole to figure out like one atom mass? Yeah, so that's what you want to be doing. So you're both using kind of that idea, right, that it's a simple cubic structure with one atom. We're given the molar mass, but we got to find one atom mass. And then density we know is mass over volume. So once we get this mass of one atom, then we can use our density to find the volume then of our cubic structure. So see how far you get from that hint then. So how's our problem going? So do we find the mass of one atom?
Yes, and what we found was 8.303 times 10 to the negative 20
8.303 times 10 to the negative
grams.
23rd, you said? So that sounds good. So I'm just setting up the calculation so you can see. So we're taking our moles divided by Avogadro's number to go to individual atoms. And so that should be what you get. And so what do we do with this number now? So we have density, we have mass.
And because we have the density, we can divide the mass of one atom by that density value to give us the volume of our simple cubic structure, which shares the same mass, which would have the same mass as that one atom. Because each corner has 1/8.
That sounds good. And then so volume, so we have this V, kind of the key is that it's a cube, right? So we have our volume equals L cubed, our length, so I'm going to fix this. Put V cubed, that should be L cubed. Or volume. So we could plug in volume, I just skipped to L cubed. But let's do, so what do we get for volume, or L cubed as I'm calling it now?
I got 2.244 times 10 to the negative 23rd.
And so that's in centimeters cubed. So did everyone get volume at least?
how many atoms?
That's the mass of one atom. Yeah, so this is just the mass of one atom, and then divide by, so that's our volume, right? So this is volume, and this is, right, of one atom, if this helps. So, right, we're still just talking about just one atom for all of these. And so now we could solve for L, right? So just take the cube root of this number. So that gives us our length for our cube. So 2.82 times 10 to the negative 8th, and I'm still in centimeters. I haven't converted anything yet. And then, what do we say? I think we were discussing it over here. What do we say the radius of our atom was equal to in terms of the length?
2 radiuses.
So 2 radius, or so 1/2 L is equal to a radius. So this was kind of the other key information that we needed, right? And this came from the simple cubic structure. So all that was packed into that little bit of detail. And so now we can solve for our radius. So divided by 2. And so this is 1.41 times 10. Again, I'm still in centimeters. And so because they asked for it in nanometers, right? I think now is a good time to do the conversion since we're in one dimension. Because, right, if you go to 2 dimensions, you have to square or cube the conversion. So like cubic, right, you cube the conversion. And honestly, I get that mixed up as well. So I'm just going to convert it in 1D. And I'll put that note. So convert from centimeters to nanometers in 1D. So easier to do the conversion. So now I'll just set up my conversion factor. I'll do it the long way. But you could do the direct conversion factor since this is 10 to the negative 2. Nanometers is 10 to the negative 9, so they have a 10 to the 7th difference. I'll go the long way. So I'll go centimeters to meters first, and then meters to nanometers. And so that should give me 0.141 nanometers for our radius of X. And so now we can do our volume. So back to what we were given. Volume was 4/3 pi r cubed. And now we're in nanometers cubed. And make sure I didn't plug anything in funny. So I get 0.0117 nanometers cubed for the volume of our element X. You have a question?
I'm kind of confused, like, why is this number, okay, like, before we got 2.24 times 10 to the negative 23rd centimeters cubed, like, what is that representing? 'Cause
So-
I'm also
Yeah, that's your L of your cubic structure, right? So when you have like your crystal structure, you have what's called like your unit cell, right? That's a square. And so that corresponds to the L. And then that's where you have to look into, right? Is it simple cubic? Is it face centered, body centered? So then it's like how many atoms are in this cube, right? Because it's all like, they're all of the L length, but then with the simple one, we just have one, and then, right, so on and so forth.
And in the test, you also, you provide us with the volume formula for the specific atom.
Yeah, so for this one, I'll give you the volume formula for that, and of course the density, and then you'll have to figure out kind of the other steps from there.
If it was more than one atom, what part of this, like,
This part, so where we find the mass, so yeah, because right, the mass is related to the density, so our mass is also related to how many atoms we put in there. Because I think we did one, now I forgot, because we had done a similar problem, but remember we had multiplied by 4 in that one? Let's see if I can even find it. Yeah, we had done kind of a similar one here. Remember this one with copper and the face-centered cubic, and we said that one had 4 atoms, so when we did the mass, we did 4 times the molecular weight before dividing by Avogadro's number. So, all right, so the last bit that we didn't talk about was just the MO diagram. So there will be an MO diagram. So if people want to stay, we can work through an MO diagram. If you want to leave, feel free to leave and slip out, that's fine.
are you gonna upload these notes?
I put a live link, so it should be updating live. The quick thing I'll say for the MO diagram is I'll at least write your XP mixing versus your no mixing.
Oh,
That-
so you'll say if it is or isn't.
Yeah, so I'll say that, and I was just going to write out the rough diagrams right now for y'all, and then if people want to leave, you can, or I'll certainly stay. And so right, no mixing. We just fill up in our normal order, and our sigma PZ is lower than our pi. So Px, Py. And so just be prepared to fill it in. And then you might also have to write the electron configuration in terms of this. So just labeling how many electrons are in like the sigma S, so sigma S antibonding. So 1, 2, 3, 4, 5, 6, 7, 8. And then with SP mixing, right, they just swap those 2 levels. So then we have our pi bonding, Px, Py, and then our sigma bonding with our mixing, and then pi anti-bonding, and of course our really bad sigma anti-bonding. So as long as you have kind of the general outline, and then of course you can just fill in, write your MO diagram. I will specify, like y'all asked, whether you can invoke mixing or not, so you don't have to figure that out.
I do have one question, and I know it might not necessarily be applicable to the exam. But I was wondering, I know that the Lewis dot structure has its own limitations. I was thinking about it, and I realized a lot of our examples so far have just used the S and the P orbitals and those energy levels. And I was wondering if it's still as effective for like the D orbitals or way down to the F orbitals as well.
Yeah, it's absolutely effective. So that's like inorganic chemistries where you invoke all the d orbitals. And then some inorganic / materials do the F. So yeah, but it's all like the same, yeah. So you just continue like building upon these fundamentals as you go on and on to chemistry. All right,
cubic radius and the SI, which is Different.
I'm not sure I have some handy, but I'll see what I can find. Yeah. And then, so London interactions, sorry, there's questions online. So they might be in the test in terms of like what bonding, so don't forget that our London dispersion is the same as our van der Waals. And so, right, these are found in every molecule. And so everybody has London dispersion forces. And then the next strongest, right, is the dipole-dipole interactions, but that only comes from polar molecules.
Hydrogen bonding is any of the really electronegative atoms attached to a hydrogen.
Yeah, and then hydrogen bonding, it's only though nitrogen, oxygen, and fluorine.
Okay, got it.
Yeah.
That row.
Oh my gosh. Dipole. Comment in the chat, dipole gives me mad human centipede vibes. That's so funny. I have watched Human Centipede, unfortunately, but yeah, dipole though is just polar molecules, so like acetone, or I didn't draw acetone, but this is formate.
Not that problem. I started and I was like, I have no clue where this is going.
PF3 would be another
I just thought it was
dipole.
like, wait, okay, so we have benzene, right? And that's like, I think that just made me realize how important units are, though, right? Because if there were none of the units there, I would not have thought that, oh yeah, this density is meant to get the molecule quick. I would have just been like, but no, like, wait, if you flip this over.
And so I was looking at the quizzes, especially if you sent it in. So HCl, right, that's another good one with the dipole-dipole interactions, but no hydrogen bonding. Did that cover your question?
That's the fun thing about math, when you have like just that equation at the right level where it's not impossible but not too easy, and you're just like quitting your frame together trying to piece it up.
All right, and then feel free to email me if you have other questions as well. I can meet on Zoom or in person. Just let me know.
Like all the pieces come together.
All right. Looking for other questions on the stream before I end it. Thank you for being here. I just want to make sure I got all the questions before I end it.
Yeah, I agree.
Did you go to the ASG meeting?
Yeah, that's why we were late.
How was it?
It was pretty good. Well, obviously I helped put it together, but it had a pretty good turnout. There was about, I think, like 8 individual students came live. Most of them stayed for 30 minutes at a time. Darren was there, of course. There was Michelle Gray from counseling, Anisha from Book Central, and of course Chelsea was there, as well as Tiffany. I didn't give too much talking, I was mostly there supporting, and then of course Phoenix was there. Nobody else from chemistry came, but
Delays the class so we can go. Nah, nobody goes anyway. More pizza for us. There was pizza. There's no way, unless everyone like gobbled it up, yeah. There's 2 of each.
Yeah. I could go around with, hey, students, you guys need to come.
Well, you're the only reason I knew about it, so I'm very glad that you said something.
Well, I was hoping Camilla would go, because we had a really good, like, earth class here at SOU. They were actually talking about how, like, ASD funds could be used to, like, create positions.
I mean, that's what I was thinking, like, these funds would eventually, like, they might, the expanding of that government in a way to serve us will eventually lead to, like, clubs and stuff having greater funds and all these different development things.
My biggest criticism of RCC is like, it's not really having like top-down admin, it's like
No, that's what they seem like. They're like, oh, you can't give out survey because your students have survey fatigue.
Nobody's received a survey from anything related to the college for over 2 years.
I've been here.
It's the groups and the groups and they're problems. And they're trades. We get told it's bad. That's the survey your students. Like, you know.
That's really weird.
Yeah, no, like, that's what this is. They're like, yeah, you actually can't survey that because they've had too many surveys. Meanwhile, me having done 0 surveys.
I kind of makes me more comfortable that there's so active on having surveys.
I just don't understand why, of all things, you want to outlaw.
Yeah.
Surveys?
Really?
I have a lot of suspicions, but yeah, I feel like the students have been having greater ways and I think I've made a lot of positive changes.
Yeah. And the big thing is having those like incentives for students, because it's hard being a student and being a student government and
It seems like
possible
too
to many
material, like it should be
being a student here
a
is
critical
so
or.
not the
Really?
average. A lot of students here are.
Like slow it down.
Students, especially some of the medical students.
Yeah. Yeah, because like, why did we test on lab stuff that we haven't used in like, I can't, like, all of the last half of lab, we were just learning.
Yeah.
can't remember that much.
And it's really, it really is difficult.
We should have nothing to come with it too.
So, yeah, we don't, it's not like.
I've complained a lot.
I know Darren's talked about it before.
Yeah.
I know that Paris gave a speech on fact.
Yeah.
Paris talked about it. But Paris had said that your speech that you gave for the BOE was
Cause I only,
I think
only
was
extra
trying
part was
to
the like,
prioritize it.
yeah, and then, yeah.
Unfortunately, it's something
And
that's
then
sort
you
of
have
falls
the,
to
like,
the side just because, Paris has the stuff.
Yeah.
Recently just got a position from
Yeah.
Tiffany. She's in that position now. And we have six officers on the back for the police. And so, yeah, they, yeah, in fact, they mentioned it, but during COVID, they cut the Asian budget by 40,000.
And drop the
So there used to be two,
Yeah,
there used
yeah.
to be two Chelseas.
Well, I was
One
thinking,
of them was
because
specific
someone
to
just
Jackson
didn't do
County
well
oversight. And they cut
on
that
the
position.
take home portion specifically, I would be like,
$50,000
hey,
of funding.
if we did some
And
practice,
they've been
like
slowly
if we turned in
decreasing,
some
because anytime
practice
we don't
questions,
spend all of our
and just
funds,
not for its whole class,
it goes back
five-
into the general
five
fund,
points
and
of extra
we
credit,
are
you do, like,
basically
2
penalized for not
more
spending that.
practice.
It's a decrease in the next exercise. Which is, I don't think it's great.
You should buy useless things in order to make sure that your budget stays the same.
Exactly. It's
What?
encouraging that financial behavior, which is.
Oh, God.
Yeah, you see a lot of that in like.
Yeah.
Like, we must spend every penny.
Yeah.
Well, we could use this for better.
Yeah. And it has stuff to do with like fund prioritization and all that.
I would have been like
If it's
on
not
the
operated
edge.
much.
Yeah.
Of an end, and I would be.
It's really
Our system is really weird, like, it bugs me when I'm looking at it, it's like, they want to act like they're a company that makes profit, but for all intents and
And we don't, and we do not hold that.
Yeah.
We are super deficit.
We're projecting to make a profit, but we're also a community college that just kind of wants to teach people, and it's like,
I just started dumping terms. Yeah, hi. I started dumping terms. I find so many in those sentences, and she just circled the one she wanted to say.
Somebody's gotta be involved.